This is the brief on the mathematical and physical relationship between the electric field and current density within anisotropic media. So, what's this all about? We're diving into Ohm's law, but for some really interesting materials called anisotropic media. These are substances where electrical properties, well, they change depending on the direction you measure them. And to really get a handle on how the electric field and current density relate, we need some more advanced math, specifically rank 2 tensors. Okay, first up, the big physical difference. In these anisotropic materials, the current density and the electric field are not always parallel. That's a huge deal. It means the current doesn't necessarily flow in the same direction you apply the field. Second, how do we describe this mathematically? Well, this non-parallel relationship is where that rank 2 tensor comes into play. We write the current density as a linear function of the electric field using this tensor, which basically acts as a map, connecting the field's direction to the resulting current's direction. The equation looks like this. Ji equals sigma ij times Ej. And finally, do they ever line up? Yes, but only under a very specific condition. The current density and the electric field only become parallel when the electric field is pointed exactly along one of the material's principal axes. Think of these as the natural, easy flow directions within the material itself. This framework provides the essential mathematical basis for analyzing current flow through materials where directionality matters.